Standard electroplating relies entirely on external electrical current. You submerge a conductive material into an aqueous bath and apply continuous voltage to force metal ions out of the liquid and onto the cathode. That reliance on external electricity creates strict physical limitations. Electrical current follows the path of least resistance, meaning it distributes unevenly across complex geometries. It struggles to reach the inside of deep cylinders, and it fails if the substrate you want to coat is non-conductive. Electroless plating bypasses these limitations by removing the power supply. Instead, the process relies on a chemical reduction driven by the internal redox potentials of the chemicals themselves. Redox potential being the measure of a chemical species' tendency to acquire or lose electrons. Creating this environment introduces a difficult chemical paradox. The aqueous solution must be thermodynamically unstable enough that it readily reduces metal ions into solid form, yet kinetically stable enough to prevent those ions from spontaneously precipitating into a useless metallic sludge. To maintain that balance, we have to construct a perfectly tuned electroless system from first principles, adjusting the exact concentration of every molecule. Eliminating the power supply shifts the burden of process control from physics to precise chemical determinism. The mechanism driving this process occurs at the microenvironment of the solid-liquid interface, the exact boundary layer where the bulk solution meets the bare substrate. A reducing agent oxidizes at the solid surface, liberating electrons onto the boundary. A dissolved metal ion captures these electrons, reducing into a solid atom anchored to the substrate. This new atom becomes a fresh catalytic site, drawing more ions to build a continuous lattice. This self-sustaining loop powers the chemical deposition, but because there is no external voltage to force the initial reaction, this sequence cannot begin if the starting surface is non-reactive. Many engineering materials, like carbon fiber, are highly inert. Their surfaces naturally repel this type of localized electron exchange. To plate these materials, we must perform a surface activation pretreatment. This process artificially seeds the inert substrate with initial catalytic sites, creating the required thermodynamic foothold. One primary method is chemical sensitization using a mixed colloid of tin and palladium. A colloid is a mixture where microscopically dispersed insoluble particles are suspended throughout another substance. During this treatment, palladium particles anchor firmly to the substrate. Palladium is highly catalytic, providing the precise surface energy required to oxidize the first wave of reducing agents. The density and distribution of these palladium nucleation centers dictate how the metal will grow. A higher density of active sites forces the metal to nucleate evenly across the surface, resulting in a uniform coating with a refined grain structure. Surface activation renders a passive geometry into a reactive state, primed to initiate the chemical engine. Once the surface is active, we need an electron donor. In nickel-based baths, sodium hypophosphite is the most common reducing agent. Hypophosphite molecules oxidize at palladium sites, releasing electrons that reduce nickel ions into a solid layer. Simultaneously, elemental phosphorus embeds into the matrix. This inclusion disrupts the standard nickel lattice. As phosphorus increases, the grid loses its order, creating an amorphous, non-crystalline microstructure. This specific redox pathway also generates a continuous byproduct, hydrogen gas, which bubbles rapidly at the solid-liquid interface. The choice of reducing agent re-engineers the material phase of the final deposit, allowing engineers to dictate the metal's specific hardness and corrosion resistance through chemical selection. If an application requires pure, highly crystalline nickel films without phosphorus inclusion, the bath requires a different electron donor, such as hydrazine. Visualization shows how hydrazine concentration dictates morphology. Above 0.20 molar, metallic growth becomes chaotic. As concentration drops to the 0.02 to 0.10 molar range, chaotic spikes vanish, replaced by a densely packed, smooth metallic surface. Maintaining this strictly lowered concentration limits the rate of electron supply. By throttling the reduction speed, the nickel atoms are given the necessary time to arrange themselves into orderly, flat crystalline structures before the next layer forms.
In electroless systems, molecular concentration functions as a direct physical lever that controls the architecture of the atoms. Returning to the core paradox of the bath, we have highly active reducing agents and free metal ions sharing the same water. Left unchecked, they will attempt to react with each other everywhere at once. If that happens, the system experiences bulk precipitation. The metal ions reduce directly in the fluid rather than on the activated substrate, instantly degrading the entire bath into solid waste. To prevent this, complexing agents, or ligands, surround and encapsulate free-floating metal ions, chemically shielding them. D-gluconate ions act as a chemical leash, limiting free ion concentration. The ligand only releases its grip upon physical contact with the active surface, strictly bottlenecking the deposition rate. D-gluconate also performs a secondary, equally vital function. It buffers the pH of the bath. Maintaining a weakly alkaline environment, specifically a pH between 8 and 9, preserves the exact redox potential needed to achieve high current efficiency. Current efficiency measures how much of the chemical reaction goes into depositing metal versus being lost to side reactions. In optimized D-gluconate baths, it reaches up to 96.4%. While the reducing agent powers the chemical engine, the complexing ligands are the brakes, ensuring the reaction occurs only on the target geometry. Chemical composition alone isn't enough to reach industrial standards. We must manipulate physical kinetics, primarily by elevating the bath temperature to between 85 and 95 degrees Celsius, which accelerates the deposition speed. However, pushing the speed resurrects the hydrogen byproduct issue. At higher temperatures, hydrogen gas bubbles form so quickly they begin to cling to the substrate. If a bubble remains stationary on the surface, it physically blocks the active site. The metal grows around the bubble, permanently baking microscopic voids into the film, resulting in high internal porosity and a weak coating. To clear this chemical bottleneck and prevent defects, engineers introduce high-frequency ultrasonic vibrations directly into the fluid environment, creating intense physical micromixing. Research by Wang and Wang demonstrated that this ultrasonic cavitation, the rapid formation and collapse of vapor bubbles, physically blasts the hydrogen gas away from the nucleation sites before any voids can form. The quantitative data is conclusive. By violently scouring the surface, internal porosity is driven down to 0.03% of the total coating volume, securing the structural density required for sensitive applications, like X-ray mirror molds. When the chemical optimizations reach their limits, aggressive physical manipulation takes over to enforce structural perfection. Holding this balance of pH, temperature, and ligand-encapsulated ions is impossible to sustain manually over long production runs. As metal and reducing agents are consumed, the bath chemistry constantly drifts. At an industrial scale, the process relies on automated closed-loop control systems. These systems track the variables in real time, integrating mid-frequency vibration, while automated dosing pumps continuously inject specific ratios of fresh nickel ions, reducing agents, and pH adjusters directly into the active flow. This relentless automated stabilization prevents the chemical parameters from drifting, enabling the continuous growth of thick, functional coatings that exceed 200 micrometers. Achieving scale in electroless plating relies on how precisely an automated system can sustain this controlled thermodynamic instability over time. Every phase of the process serves a rigid function. Surface sensitization constructs the initial arena. Reducing agents supply the electron power, and ligands enforce the chemical rules. The absence of external electricity demands absolute chemical precision, where the slight adjustment of a single additive definitively alters the atomic outcome. By mastering this balance, engineers execute uniform deposition across deep cavities, non-conductive plastics, and complex aerospace and optic components that traditional electroplating physically cannot reach. Electroless plating operates as a system of engineered thermodynamic equilibrium, building impenetrable metallic structures, one isolated atom at a time.